we're at a phase now of the development of AI where things can go much faster than we're used to from historical precedents.
Ultimately, we want to solve scalability for neural networks far into the future.
If you solve continual learning for transformer type networks, then suddenly you would have systems that just keep on learning and adapting progressively with every interaction, which doesn't in itself give you AGI, but it's a step toward AGI, right?
We are looking into other methods like predictive coding that we think will provide a better framework for models that continually learn.
You're still doing gradient descent. You're just arranging some loops in a different order, right? It's not that weird.
Welcome and greetings, Singularitarians. It's wonderful to have you here on our renewed Tech Tuesdays. It's great to be back diving in with our researchers and deep tech innovators to talk about all the amazing things that we're building here, products, projects, technologies, innovations, changing the world, building BGI. I'm honored to be here today with Ben Goertzel, of course, our amazing CEO, coined the term AGI, has now coined the term BGI, and we need to bring that out into the world.
From AGI, BGI, what comes next? Yeah.
CGI.
No, it's Omega Claw, right? So,
Omega Claw. Omega GI.
yeah, there you go. Yeah.
And Matthew Behrend, one of our amazing research tech leads, PhD, and all-around brilliant individual who's joined us here to work on our predictive coding team and has now helped us launch or built and launch this FabricPC tooling for the community. So it's wonderful to have you both here. Thank you for joining us. And I think that a great spot to get started is just to look at how machines learn currently. Maybe, Matthew, you could dig in a little bit about our current neural network learning technologies so that we can set the stage for how predictive coding is different.
Hi, folks. Great to be here with you. Pleasure to share the time with Ben and Haley. Yeah, so, right now, basically almost all models in AI learn the same way, by backpropagation. It works. It works brilliantly well, and it's very efficient for matrix computations on current hardware and GPUs. But this one method dominates the field completely, and its limits become the entire field's limits. So we're actually seeing, larger and larger data centers being built. They're competing with, human water supplies and residential energy. And we think that this is ultimately not going to scale well for society and for AGI itself. So we are looking into, other methods like predictive coding that we think will provide a better framework for models that continually learn and scaling.
Thank you so much, Matthew. Yeah, absolutely. And then backprop, of course, has some very known limitations that we're dealing with, seeing the result in with LLMs and other types of neural networks growing popular. Can you dive into those just a touch?
Yeah. Well, backpropagation works by taking the error at the output of a neural network, and then by the derivative chain rule, propagating that back to every previous activation layer in the network, and then to the weights of each of those layers. That requires computing every layer of the network in sequence and waiting for all of them to finish computing before updating any values at any of the intermediate hidden layers. Predictive coding works by doing all this in parallel. Errors are actually computed at every layer, and signals gradually trickle through the network from the endpoints. And this allows all the nodes to be computed in parallel. It also opens up new structures that are not sequential.
Thank you so much. Yeah. Looking at how backprop has this limit of scalability, right? If we have to use the whole neural network to learn anything, and it has to go all the way forward, all the way through, and we're looking at gigantic parameters these days, then this is clearly a system that just on that alone is going to be problematic in the future, as well as its specialization. Ben, do you want to provide your own contrast between backprop and predictive coding?
Yeah, sure. And I mean, I would say starting at an even higher level. I mean, there's going to be many different approaches to AGI that can work, right? And neural net based is one very promising category of approaches. There's another category of approaches like Hyperon, which combines neural nets with logic and evolution and so forth. But when you look in the neural net space only, there's been a huge variety of neural net architectures and learning algorithms, throughout the history of the neural net field. Since, neural nets were introduced as a formal model in the 1940s, right? Then the backpropagation algorithm was published in the late 50s. Then you had evolutionary neural networks. You have Hopfield neural networks, which use Hebbian learning and organized strange attractors. And predictive coding is an alternate way of training neural networks, has been around for decades also. So there's a richer pool of ways of structuring and training and inferring using neural nets than many current practitioners recognize, because one way of training neural networks, which is a backpropagation algorithm, showed enough, practical success on some real problems, like within convolutional neural nets for vision processing, or now within transformers for next token prediction. It's been successful enough that everybody jumped on that bandwagon, right? And business tends to be that way because investors tend not to like to invest in stuff they don't know works. So when they see something that made someone money, they're like, me too, me too. And science tends to work that way also, partly because of grant funding dynamics, because the folks giving out grant funding like to bet on stuff that they already think will work. So you have a dynamic where once something shows promise, everyone piles on and they forget there's a lot of other things showing early promise too that may just have not gotten quite as much resourcing. So we've seen what I think is a premature lock-in on backpropagation as a way of training deep neural networks. And this has had some consequences that feel absurd to me, having grown up around, a greater variety of neural training methods. Like backpropagation doesn't work that well with recurrence. And it's not hard to see why. Like you're taking the error coming to the top level of a network and then saying, well, to make that error, how much error would have occurred here? To make that error, how much error would have occurred here? To make that error, how much error would have occurred here? But when you get a lot of cycles in the network, this kind of calculation becomes brittle and errors blow up. So as a result of backpropagation not being great at handling rich recurrence, well, instead of switching to a learning algorithm that's better at handling recurrence, we've just said, okay, let's build neural nets with minimal recurrence. And, this necessity being the mother of invention, this has led to some brilliant things, like transformers have an attention mechanism that is a limited form of recurrence that's quite valuable. But on the other hand, the brain is way, way more recurrent than a transformer or CNN or any of the popular forms of neural network. And we haven't really explored the space of richly recurrent architectures because of backpropagation's limitations in converging on this sort of architecture. Continual learning, as already mentioned, is another point. Like we take for granted now that after you train a neural net a certain amount, you got to freeze all the weights, or else the thing will start to degenerate rapidly, catastrophic forgetting and its cousins, right? But again, this is not a necessary property of neural learning, right? It's a shortcoming of the backpropagation algorithm and some other classes of algorithms, and there are neural learning algorithms that can keep on learning. And back in the 90s, my friend George Christos and I published some work showing how to make Hopfield nets do continual learning, right? And so that there is a whole literature there. And if you solve continual learning for large neural nets doing, say, next token prediction, then you would get rid of this thing where you freeze, like, okay, here's the 5.5 model or the 4.8 model, and everyone has to use this frozen model, and it can do very limited learning only in the activation space in the brief context of an interaction, right? If you solve continual learning for transformer type networks, then suddenly you would have systems that just keep on learning and adapting progressively with every interaction, which doesn't in itself give you AGI, but it's a step toward AGI, right? Like it's a property that human-like AGI systems should have. So that there's a whole bunch more one could say, but there's a bunch of limitations that come with the backpropagation algorithm, which we accept now because it has led to a whole, tooling industry, a whole stack down to the hardware level that contributes to making it relatively fast to train backprop based neural networks at a huge scale. But I think it's time to break that hegemony and open things up to other ways of training neural nets. And as a final point, I'm reminded of a friend of mine 20 years ago, it would have been. He was trying to start a company using deep neural networks to do speech to text. And like the gorilla in that field then was a company called Nuance. And Nuance wasn't doing deep neural nets at that point. They were using a simpler statistical pattern recognition approach. And my friend just couldn't get his deep neural net approach as good as Nuance was, because Nuance had put literally billions of dollars into training this statistical method. It was clear deep neural nets were better than statistical methods, but they just had so much data, they had so many machines, they put so much time into it, and he never managed to do it. He pivoted to finance and then to vision and other things. And eventually Microsoft actually were the ones who came up with the first neural net speech to text that beat statistical methods, and then everyone jumped on board. So I think we're sort of in that position now with other neural net learning methods versus backprop. Like backprop isn't really the best way any more than Nuance's statistical speech recognition was the best way back then. It's not the best way, but there's been so much put in to optimizing this fundamentally suboptimal way that we still have to play catch up for a while, even with other methods that are fundamentally better. So, I mean, there's a bunch of math explaining why predictive coding is a better way to do neural learning than backprop. And there's a biological line of argument also. I mean, predictive coding neural nets are not precise biological models, but they're much closer to how the brain works than backpropagation is. I mean, they're doing localized learning so that each neuron and each weight are learning on their own, and that learning then coordinates with everything else in the network, whereas backprop sweeps through the whole network in a very non-biological way. So there's a lot to be said for it, but we need to do a bunch more research to do all the tuning and fiddling to get the results to be better than backprop on practical cases. And that leads to the next chapter of the story, which I think Matt would be the one to tell, like why FabricPC was developed as a way to sort of smooth out and make more efficient the process of doing all this experimentation that we need to do to make this alternate way of training neural nets pragmatically demonstrate the theoretical and conceptual advantages that we already know are there.
Matthew, your lead in, please share with us y- your perspective, why you built Fabric PC, what differentiates it, and what it compares to in the predictive coding development and research space.
Like Ben said, predictive coding is it's a locally learning method. So, the brain is thought to learn locally rather than trying to backpropagate errors through an entire chain of neurons. And predictive coding has actually been around for a long time, for several decades. But once neural networks got a lot of attention, started gaining ahead in success, then like the field really locked onto it. And so predictive coding algorithm hasn't seen as much of the development that's been poured into a recent year after year of conferences in optimizing backpropagation for neural networks. So what we're seeing is that there's a need for a framework that allows us to experiment in predictive coding, put that energy into developing, the techniques that make it work well. Like in typical neural networks run on backpropagation, we've learned how to initialize the weights properly. We learned, a Chi-Ming initialization and Xavier initialization, so that signals don't explode and we don't have exploding or vanishing gradients through the network. Predictive coding, we've just learned recently how to do those things, and you can see those advantages in the literature. And FabricPC is dedicated to providing a way to accelerate our research, both in SingularityNET and in the community at large. So we're pulling state of the art off the shelf from developments in other research labs in predictive coding and integrating those into FabricPC. And we've created a library in SingularityNet that is useful for running these experiments, for advancing predictive coding algorithms and neural networks, as well as developing new models and conducting research. So we're really excited that we have a few groups within SingularityNet uh, working hard on solving these problems. And we welcome everyone in the community to come build with us.
Thank you, Matthew. Can you talk a little bit more about who would be the users of Fabric PC? Who's this geared for?
Everyone who's an AI researcher and has some interest in alternatives to backpropagation, interested in pushing the envelope, where can we look at algorithms that open up new avenues for new architectures like graph-based architectures, recurrency? These are things that backpropagation doesn't handle well, but are a natural fit for predictive coding. So we have associative memory as a there's a built-in node to FabricPC that you can compose into neural networks with other transfer functions.
That's fantastic. Thank you. Yeah. And you've really put this tooling together in a very robust way. There's a number of demos for the community to get started on, great documentation on how to use everything. I've spun it up and run it. That's how accessible it is. And it's fun too. Can you talk about some of the ideas, some of the demos, some of the things that people, researchers can do with Fabric PC to push the envelope and explore this area deeper?
Yeah, we have a ResNet 18 demo on CFAR 10, so you can open that up, run it, train the model from scratch, and tinker around with it. It's a very natural interface for composing networks with nodes and edges, and it looks a little bit similar to things that you would do in Flax or PyTorch, but it's fully graph-based, so it's really easy to compose arbitrary networks, things that you wouldn't be able to do normally in sequential.
Thank you. And then I'd love if you could share just a little bit about hackathon at our recent meetup in Ethiopia at the ICOG Labs, our office in Ethiopia. And some of the researchers there came up with some brilliant solutions using Fabric PC. Maybe you could touch on some of those.
Yeah, we had some awesome work come out of the Otis hackathon that we did for Hyperon. So we had 11 of our developers in ICOG come up with their own projects and go from idea to completed working code with data and results and a pitch in just half a day. We had a team working on natural gradients using the Navier-Stokes incompressible flow equations to optimize gradient and updates for learning weights. And then we had a couple teams working on improving our transformer models. That's an active area of research of developing a small transformer model in FabricPC as well. And we had a couple other teams with really cool original ideas. So yeah, really proud of the work that they turned out in such a short order with great quality.
Thank you. It's so amazing to have this group of researchers who's working on predictive coding, and they could take up this tool and move it forward in such a short amount of time. And then its ease and ability to be used lent to that as well. So I understand currently backprop, we still have a ways to go to get this to the level of capability, speed, and these things that current neural networks have, backprop neural networks. But looking at that, this is the current, right? We're building toward a future, right? How does Fabric PC, how does predictive coding meet? Can you dive a little bit more into how this meets the future of chips and efficiency better than backprop does?
Well, on today's hardware, we know that predictive coding takes longer to run on GPUs. What we're doing is looking towards the future and connecting the dots to future hardware when eventually we'll have neuromorphic hardware, non-von Neumann compute, things where we can run the network nodes in high parallelization on very energy efficient hardware. And we want to be ready for that future and help build that future. So that's why SingulariNET's investing in FabricPC, which is infrastructure for predictive coding and for this research. The other thing that we're thinking, the brain is also very efficient. It's not as energy hungry as the hardware we're using today. So while we're not trying to copy biology here in any way, we do take inspiration from it. And predictive coding is an algorithm that was born out of neuroscience. It's an algorithm that was is a way that the brain is thought to possibly compute and learn. And if we can draw inspiration from that, come up with ways to run our models and train our models more efficiently, and if we don't have to scrap all the weights every time eventually in the future, and then that opens up huge gains for model capability as well as efficiency. And I'd love to hear more from Ben too on the the brain inspired thinking and how this fits into the overall architectures that we're building.
Yeah, there's a few different aspects to highlight in addition to everything you said, which made a lot of sense. I mean, one point is the localized aspect of learning in a predictive coding network is highly amenable to distributed and decentralized processing, right? So, I mean, of course, with backpropagation, you can train across many machines, but they got to be really closely coupled together because you need to coordinate the learning. Whereas in FabricPC, I mean, you will benefit from that, but in principle, I mean, predictive coding of a big neural net can be done with parts of the neural net on different machines, tied together in a decentralized network with heterogeneous processing and heterogeneous connectivity. And I mean, you'll still be better off, with maximal processing in a maximally tightly connected network. But you can do a lot with a variety of different infrastructures, and that's certainly a big plus. I would say for something like Hyperon, where you're connecting deep neural nets with logic engines and evolutionary learning and other such methods, also the localized nature of predictive coding is a big benefit because due to the learning being localized, the semantics tends to modularize better also, although there's a bunch to study there and a bunch of research to do there. But if the semantics is better modularized and localized, you can better link like part of a logic network in with a modest sized sub network of a neural network, right? And so you get neural symbolic interfacing to work better. So it's totally true what Matthew said. Like as hardware evolves, if hardware is not optimized just for backprop, but hardware is optimized for predictive coding, then you can run predictive coding very, very effectively on appropriate compute hardware. It's also true that the game isn't just about like training the neural net most efficiently on one machine in isolation. Like it's also connecting the neural net with other sorts of AI tools, and how do you better leverage, networks of different sizes and connectivities. And there's a lot of these places where predictive coding has an intrinsic advantage. So as one example among many, I mean, we're already doing early experiments on how do you put neural nets inside Hyperon's Mork knowledge graph along with neural nets, right? And FabricPC doesn't yet support that, but it can in a future version. And you can do it with predictive coding and with the FabricPC way of thinking. And I mean, you can't do that with backpropagation. So I think the current reality is already very cool. And I think we're probably quite close to a number of different people using FabricPC to train predictive coding models that dramatically outperform backprop on various special cases. Like, I mean, I don't think we're too far from that happening. The whole world has put absurdly little effort into this sort of thing in the past. And one of the gating factors has been the lack of sort of professional, scalable, convenient ways to run the experiment. So now that we have that, I don't think it's very long before we see the first few breakthroughs of, whoa, PC is doing this way better than backprop. So the near term is already very close at hand, and you'll need something interesting. But then I think we also have a clear path forward to make things yet more interesting than that in terms of PC-based neuromorphic hardware, as Matthew said, in terms of tight integration between PC networks and Hyperon and rollout on decentralized networks and so forth. So there's we're at a phase now in the development of AI where things can go much faster than we're used to from historical precedent. So I think we'll see things go pretty quickly from here to initial practically highly valuable results to then whole new frontiers being explored.
Thanks, Ben. And then perhaps you can speak to this. We've focused largely on symbolic type methods, graph, atom space, and Mork, PLN, ECAM, these types of things. And we haven't piled in on the neural network side. Why did we move to PC, to our own sort of neural
Well, I
network?
mean, I used to, it's funny if I go back to the late 80s when I was a PhD student, I was trying to do a PhD thesis on recurrent neural nets for time series prediction, and I couldn't find an advisor because it was too weird. Like, I mean, I was in the math department. I couldn't find an advisor in the computer science or math department. I found a guy in double E department who would do it. Then I would have had to become an engineer, which was not what I wanted because you had to stay in school too long, right? And then I was teaching recurrent backpropagation at University of Western Australia in the mid-90s, right? And then in the early aughts, did a whole project for some US government agencies using chaotic Izhikevich neurons to model how 7 different regions of the brain helped geoint analysts find the terrorists on the map, right? So, I mean, it's not like I ever disliked neural networks. Clearly, neural net is a very interesting aspect of AI. My thinking for a long time had been the world is doing that already, right? So, like, if the optimal way to get to AGI that has a clear upgrade path to superintelligence is to put neural nets for what they're good at, together with logic systems for what they're good at, evolutionary learning for what it's good at, and so forth. If that's the best way to get to AGI, which had been my way of thinking, then I figured let's focus on the things the world is neglecting, right? And there's so much work going into scaling up neural nets. I'm like, let's leave that to these, big tech companies and major universities that are putting hundreds of billions of dollars into that, and let's focus on the other parts that are being neglected. But then at a certain point, I realized the mainstream was just doing neural nets badly, right? And like if I wanted this integrated system, you would need neural nets that are better at integrating with other things, which means that have more modular, less tangled up in internal semantics, and can play better with other sorts of AI methods. And it just seemed like the mainstream bizarrely wasn't pursuing that, right? And I then met a guy named Alex Arobia at RIT, and I really liked his work on predictive coding in particular. I mean, there's a lot of cool stuff in the PC literature, but some of Alex's papers really resonated with me as making sense. And the SingularityNET funded some master's students in his lab. We got to know Alex better, but then I realized what Alex was doing in his lab was amazing, but like a graduate department in a university just wasn't oriented toward scaling things up and making things practical in a major way. Like they were more oriented toward proof of principle about this or that algorithm variant, which is necessary and very, very interesting. But then you need a different sort of work to take things to the next level, right? And so then, yeah, we started a predictive coding neural net R&D group in SingularityNet. We've hired students from Alex's lab and then put them together with folks like Matthew, who had more of a scalable AI implementation background from big tech career histories, right? And then we're proceeding along that trajectory. And I would say some folks on our PC team are bullish that by doing PC right, you can just get an AGI that way. And if they're right, I'll be very happy, right? And I mean, we also have one of the lead developers on our PLN logic engine is convinced just get PLN inference control to work, and then that will yield an AGI, right? And maybe we will come up with many different species of AGI minds with different characteristics, put them all in a model in an AGI system ensemble, right? Or maybe the best thing will be a hybrid system where in the same mind you're connecting predictive coding with logic and other things. So I think there's a lot of different ways to create intelligent systems. I think scaling up backpropagation neural nets probably is not one of them, however. And I mean, out, out of all this, we decided to place some of our limited resources in the predictive coding area, but highlighting the importance of FabricPC as an open source platform and framework. I mean, there is a lot of work here, right? And SingularityNet, we're a sizable initiative. We're probably the largest AGI project outside of big tech, the largest AGI project outside of backprop deep neural nets, the largest AGI project in the decentralized world. But we're still very small compared to big tech companies or even to, mid-size like Anthropic or something, right? So in order for us to do what we need to do, we need to be the kernel of a broader network of open source contributors. And this is why we're putting Fabric PC out here for everyone and not just using it ourselves, right? Like we need brilliant contributions and enthusiasm, dedication, passion, and vision from far and wide to help us leverage Fabric PC to make predictive coding do what we know it's is capable of.
Thank you so much, Ben. That's a great perspective and a great layout of the landscape. And kind of along those lines, perhaps Matthew, you could start and Ben chime in. Has the rise of LLMs, their popularity, they're breaking into mainstream, they're becoming so powerful. But that part, and then also this part where they're not on that same exponential anymore. Has that combination of factors or some part of those factors contributed to maybe more interest in other methods like predictive coding? Matthew, again, you yourself did not come from a predictive coding background, but after seeing it became very, very interested and enthusiastic and built this tool for others, right?
That's right. Of course, like everyone in the field and in an industry, I've I've worked in backpropagation, and it works extremely well and scales well to a point. Some things got me really excited in the predictive coding literature as I started reading what people were doing in the recent years. There's a lot of really great work coming out of the Millage lab, out of the Buckley lab, and we recently just integrated maximal update predictive coding into FabricPC, which came out of Buckley's lab, which extends the ability to propagate signals through a predictive coding network, which previously was kind of toy examples, maybe 5 layers deep, and now signals can propagate 100 layers deep because the 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 forward projections don't explode anymore in variance. So techniques like this have really opened up the field to advancement, and that got me excited. Of course, along with the amazing quality of researchers at SingularityNET. So, we have a group of researchers here who not only are brilliant in AGI, but also really interested in understanding consciousness itself and what it means to have thinking machines. And that's the kind of research we're able to do.
And on that note, we're inviting the community to join us in building thinking machines this month in June for the BGI Sprint. Another quick plug, we can put the link in the comments, but Fabric PC is one of the tools where we're engaging people and among others, and being on this journey, being involved in this moment where the technology is accelerating development so much for PC, for non-LLM and LLM approaches, that it's incredible.
And going a little further in the future, I mean, at the AGI 26 conference in the last week of July at San Francisco State University, I mean, we will have special sessions on predictive coding and on active inference, right? So that's going over a bunch of cool new algorithm ideas and research papers, which again, exactly the sort of thing that Fabric PC is supposed to help with when you come to, you know, playing around with the ideas fluidly in practice and then scaling them up toward real world implementation. So yeah, come to the AGI conference and learn more about all the theory and what other people are doing, and you can also check it out online if you can't make it to San Francisco.
And Alex Orobia and students will be there as well, so we can
And
collaborate and
Matthew
share.
Behrend,
And Matthew Behrend,
better yet.
yes, and more of the team, of course. So, from your own perspective and what you're also seeing, Ben, what would you say? I mean, we heard Rich Sutton last year talking about backprop, of course, not necessarily looking in the direction of predictive coding, but has the rise of LLM and the tapering of LLM grown interest in alternative methods like predictive coding and backprop
Not not
alternatives?
not as much as it should have, to be honest. I would say I haven't seen a big upsurge of that in the commercial world. So I think the tide has yet to turn, right? But on the other hand, when it turns, it could turn big, right? So I mean, honestly, I think what we need is like one flagship application where, PC does something that people care about way, way better than backprop does at some meaningful scale. And once we have that, the floodgates will open and it will be much easier than getting a lot of people to jump onto Hyperon, which is a whole different AI paradigm. I mean, in the end, like, I was looking at it once and like, hold on, predictive coding, like you're still doing gradient descent. You're just arranging some loops in a different order, right? It's not that weird, but yet it's quite different in the overall system dynamics and the practical consequences. So I mean, I think we have very, very interesting results at the level of academic publications and small scale demonstrations. We need some kick-ass practical demo of PC outperforming. I think once that emerges, which could be from our own internal team or from some user of FabricPC, which in a way would be even cooler, right? Once that happens, I think the world is poised to jump because there is an understanding now that the LLM scaling curve is sort of flattening. And if you listen to even Sam Altman and, the Google people who are going big into backprop trained LLMs, I mean, there's a lot of recognition that we're going to need some additional ideas also to get to AGI. So I mean, I think the commercial AI world is poised to jump into this, but has not yet made that decision. And perhaps the Fabric PC community, as it grows, will be what catalyzes that transition.
Thank you so much. And then can you speak a little to the roadmap? What's next and coming for our predictive coding team? And do you have any intuition on what that demo is where predictive coding really shows its chops?
I thought that was a Matthew question. Is that a Ben question?
That would
I
either.
mean, for the roadmap, I will leave it to Matthew, but I mean, I'm more thinking about the longer term roadmap in terms of integrating predictive coding with Hyperon and so forth, which is coming a little later. And I've been thinking a bunch about also using Fabric PC to train a predictive coding residual layer on top of large open LLMs. So like you have a trillion parameter LLM, but then you put maybe 10 to 30 million parameter residual layer on top, which is trained using predictive coding, can do continual learning. So I've been more thinking about things that are a little outside the step-by-step roadmap of Fabric PC, which will be something for Matthew to speak to. But in terms of what demonstrations will be, I mean, we have people playing with applications all across the map, right? So, I mean, there's computer vision. We're doing some stuff with music processing. And that then, of course, there's language processing applications. I'm particularly interested also in financial time series processing, and that's a domain where the better modular causal modeling that you can get inside PC may give value in terms of making use of limited data and not overfitting. So I think we're going to see a broad community of people trying a wide variety of applications, and predicting that there will be breakthroughs is of course much easier than predicting exactly which thing will break through first.
Sounds great. Thank you. And then Matthew, I'd love to hear more about the roadmap of Fabric PC itself. And then also if there's any specific places or innovations that you would point experimenters or researchers at for how to move
Mm.
this project forward.
Yeah. Ultimately, we want to solve, you know, scalability for neural networks far into the future, and continual learning. So we have several folks working on continual learning in the ACT-PC team in SingularityNET. We have experiments running in FabricPC as well as Aurora's library. And in FabricPC, what we're doing right now is building out more capabilities to support our research and support the community to build along with us. We welcome everyone to collaborate and would love for everyone to reach out, open a GitHub issue, open a PR request. We'd love to work with you. A couple things coming in the roadmap coming up next for FabricPC are increased node parallelism, so more efficient compute on GPU hardware so that we can run larger models, things that are more interesting for doing LLMs and be able to process language at larger scale. And we also have more with associative memory coming in. So we have Storky Hopfield nodes already, and we're doing more work with bringing associative memory capabilities into the library off the shelf. And so, there's a really great paper out called Hopfield is All You Need that actually draws the parallel between transformer attention mechanisms. So, like dot product attention and Hopfield networks actually can be shown to be equivalent in mathematics. And they kind of got that to work in a feed forward network with backprop. But in FabricPC, we actually have real fixed point attractors that we can converge to in the inference phase of predictive coding networks. And I think that's going to just open up a lot more capability for new architectures for memory and attention that we can experiment with in FabricPC.
Maybe you can dive in just a little bit on the associative memory. I'm not familiar with that in this term. Can you talk a little bit towards that?
Yeah, so associative memory is it's when you have lateral connections between neurons, like the way the brain does. So in typical feed-forward neural networks, every neuron in layer A connects to every neuron in layer B, but neurons in layer A actually can connect with themselves. And so in associative memory, there's a square weight matrix where each neuron gets lateral inhibition from its neighbors. And you can iterate the the output of this layer such that it has fixed point attractors and can store a number of memories within that layer of patterns that it's learned. And then when some noisy input signal comes in, similar to how the mind works, that layer can say, okay, well, this is nearest to some memory that I've learned, and then start to iteratively converge the output towards that memory. So it effectively takes a noisy input probe, says, well, this is nearest to some memory that I've learned in my training, and then output that memory to the next layer as a meaningful feature that then informs the next layer of processing in the network.
Incredible. That's so exciting. And then one more feature I'd love to take a dive in on is that we talk in predictive coding about the opportunity for multimodal or continual learning. Can you touch just a moment on that? I know we're running low on time.
Well, continual learning is an important and unsolved problem. I wouldn't say FabricPC solves continual learning, but we think that it is a better framework for doing research in advancing the state of the art in continual learning.
You asked earlier somewhere what would be interesting things for people to focus on. So just there's an unlimited number of very interesting things to focus on, but one thing we've been thinking about recently is how to make the prediction part in predictive coding work better with the attention mechanism of transformers. Because a lot of the predictive coding literature is computer vision oriented or kind of robotics reinforcement learning oriented. There's a few papers on predictive coding applied to transformers, but they're not necessarily optimally wrapping the prediction aspect of predictive coding, where you're trying to have each layer predict what another layer will do. They're not necessarily wrapping that optimally into the dynamics of the attention mechanism of the transformer. So that's a fairly obvious and interesting thing on which there could be some creative thinking. Now, another direction I'll throw out there, just because I think it's cool, is years ago I played with chaotic neurons, like Izhikevich neurons from Eugene Izhikevich's work, and predictive coding, unlike backpropagation, can work with more dynamically rich models of the neuron that are standardly used in computer science, right? So that's another interesting area for investigation, because chaotic oscillators are good at generating time series, right? So I would think it's promising to look at PC networks for financial or biological time series prediction, where the neurons are, chaotic Izhikevich neurons rather than simple sigmoid type neurons. But that's just two among the endless variety of interesting ideas to be explored. And it's great to have, a simple to use, scalability friendly framework to do all this exploration.
Thanks, Ben. Very interesting. I do hope somebody pursues that. So, Matthew, if I can end with you, researcher goes to the repo. How do they get started, or somebody who wants to explore this tool?
Yeah, go to trueagi-io on GitHub /FabricPC, clone the repo, and then it's a pip install and run one of the demos. We have a few in the example folders that are fun to tinker with, and there's documentation available for getting started and building out custom nodes and extending the library.
Thank you so much. This is wonderful. Thank you both for being here. If there's no final words, I think we'll wrap up for the day. Thanks for the community for joining us. 2 thumbs up. There we go. Fireworks, all the good stuff. And yeah, we'll look back on this episode in a year and say this is where it all began and took over from neural networks, perhaps. Thank you for building out this tool, Matthew. Thanks for joining us, Ben, and diving deep into this topic.
Thanks all.
Thank you, Haley.
Happy
We'll see you
hacking.
next time.